Hey, welcome to The Explainer. Today, we're going to dig into a really fundamental formula in electromagnetism, the potential energy of an electric dipole in a uniform field. Instead of just showing you the formula, we're going to build this thing right from scratch, step by step.
Okay, so here's our game plan. First, we'll set the scene and talk about what happens when a dipole is in a field. Then we'll figure out how much work it takes to actually turn it. From there, we'll make the crucial link between that work and potential energy, which will lead us straight to the final formula. And finally, we'll unpack what that formula tells us about stability.
All right, first things first. Before we can do any math, we've got to get to know the two main players in this story, the electric dipole itself and the electric field it's sitting in.
So let's start with our main character, the electric dipole. The easiest way to picture it is like a tiny little arrow floating in space. It has a positive charge at one end and an equal but opposite negative charge at the other. We wrap up its strength and its direction into one handy vector called the dipole moment, which we label P.
Now, things get interesting when we drop this little dipole into a nice uniform external electric field. What happens? Well, the field pushes on the positive end and pulls on the negative end, and this creates a twisting force. In physics, we have a name for that rotational force. It's called torque. It's basically the field trying to boss the dipole around and make it line up.
But here's the thing, and this is super important. This twisting force isn't always the same. It totally depends on the angle, theta, between the dipole and the field. If that dipole is completely sideways to the field, at 90 degrees, bam, it feels the maximum possible twist. But if it's already perfectly aligned with the field, the twist just disappears. The torque is zero.
So the field is always trying to spin this dipole one way, trying to get it to align. But what if we want to spin it the other way? What if we want to fight against the field? Well, as you can probably guess, that's going to take some effort. Or as we physicists like to call it, it's going to take work.
And that leads us to the big question we need to answer. Just how much work does it take to rotate this thing from some starting angle, let's call it θ1, to a final angle, θ2? Because, and this is the key, by figuring out the work we do, we're really figuring out how much energy we're packing into the system.
Now, you might think we can just multiply the torque by the angle, but nope, it's not that simple. Why? Because the torque itself is always changing as the angle changes, so we have to bring out the big guns, calculus. But don't worry, it's pretty straightforward. We start small. We find the teeny tiny bit of work, dW, it takes for a teeny tiny turn, dθ. Then we just plug in our formula for torque. And finally, we integrate, which is really just a fancy way of adding up all those millions of tiny bits of work from our start angle to our end angle.
And voila! After the calculus does its thing, we land on this really clean result. The total work that we, an external force, have to do to rotate the dipole is right here. It's just P times E times the difference between the cosines of the angles. Okay, so let's pause for a second. We just did all this work, right? We put in all this effort to turn the dipole against the field. But where did all that energy go? It can't just vanish into thin air, and this is exactly where the idea of potential energy comes into play. And what we're seeing here is one of the most fundamental rules of physics in action. When you do work against a conservative force, like the electric force here, that work doesn't just disappear. It gets stored. It's like you're compressing a spring. The energy is converted into potential energy, just sitting there, waiting to be released. So, what does this all mean? It means the change in our dipole's potential energy, the final energy minus the initial energy, is exactly equal to the work we just calculated. We are so close to the final formula now. All right, we've basically done all the heavy lifting. We know how an energy change works. Now we just need one last little step to define the potential energy at any single point, not just the difference between two. To do that, we need a baseline, a 0 point. A sea level for energy, if you will. And by convention, basically all physicists agree this was the most convenient way to do it. We define the zero energy point to be when the dipole is perpendicular to the field, at 90 degrees. It's totally an arbitrary choice, but man, it makes the math so much cleaner.
So here's what we do. We take our work formula, we set that initial angle to 90 degrees, which means the initial energy is 0. And because the cosine of 90 degrees is 0, that whole first term just vanishes, and what we're left with is this beautiful, simple, and incredibly powerful final formula. The potential energy, U, is just negative PE cosine theta.
Now this formula, it's not just some letters and symbols on a screen. It tells a story. A physical story about how the dipole is going to behave.
It tells us which positions are comfy and low energy and which ones are precarious and high energy.
Let's just break it down. When the dipole is perfectly aligned with the field, that's at 0 degrees, cosine is 1. So the energy is at its absolute minimum, negative PE. That's a state of stable equilibrium. Just think of a marble resting at the bottom of a bowl. It's happy there. Now, what if it's pointing the exact opposite way, at 180 degrees? Well, then the energy is at its maximum, positive PE. That's unstable equilibrium. That's like balancing that same marble on the very top of an upside-down bowl. The slightest breeze, and it's going to flip right over.
And that really leads us to a final, much bigger question, doesn't it? If everything in nature wants to get to the lowest possible energy state, like that marble in the bowl, then why do high-energy, unstable states even exist at all? This whole idea of stable versus unstable energy, it's not just about dipoles. It applies to everything, from a log of wood waiting for a match to the fundamental structure of the entire universe. It's one of the big, beautiful puzzles of energy, and really, of existence itself.